Hello everyone, welcome to my video on global extrema. So in my previous video we saw the extreme value theorem and we saw Fermat's theorem. So what we're going to do today is we're going to combine those two notions and we're going to go find our global extrema, which is essentially the absolute maximum and minimum. Okay, so here we have our strategy to find the absolute max and the absolute min on a closed interval. So we call this the strategy for the closed interval method. Okay. So in order to find the absolute max and the absolute min of a function, I should have stated a continuous function on a closed interval AB, we must have these three, we follow the following three steps. So the first step is find the critical value. So f prime of c equals 0 or f prime of c doesn't exist. Those are the two cases that we have. On the open interval AB, and then find their corresponding y values. So you go ahead, you find your critical values, your critical points, the values c, and those correspond to x values, and then with those x values you go find the y values by substituting it back into the original function that's given. Okay, so we find their y values. Step 2, find the corresponding y values for the endpoints, namely f of a and f of b. So once you have your endpoints, the closed interval that's given, a and b, go find their corresponding y values. And then step 3 is to take the absolute maximum in between the first and the second step. So if the largest value ends up being on an endpoint, you have to consider that. Okay, so step 2 is very important, where you have to consider the endpoints because the absolute max and the absolute min can occur on the endpoints. Okay, so let's take a look at a couple of examples. So in this first example over here, we have to find the absolute maximum and absolute minimum of the function f of x equals x cubed minus 9x squared plus 15x minus 5 on the closed interval from 0 to 6. So this is a polynomial function, it's continuous, that's one of the criteria that we need continuity, and 2, we have a closed interval from 0 to 6. So the two things are satisfied in order to use EVT. Okay, so let's follow our strategy. Another thing I just want to mention, you could also use Desmos. Just at the end, once you find your solutions, use Desmos, look at your answers and see if they compare to the actual function on Desmos. Okay. So let's start off by finding the critical values. So we take the derivative, set it equal to 0. So the derivative of this function is 3x squared, it's just power rule, minus 18x plus 15. Okay. Okay, so we got our derivative, now we have to set it equal to 0. Setting this equal to 0, we have to go find the x values, or what we call the critical point, so we could replace it with c. So we have 3. I'm just going to use the parameter c. I'm going to factor out a 3 because 3, 18, and 15 are all divisible by 3. So we're left with 3. I'm going to just rewrite c squared instead of x. If you want to leave it as x, that's fine. I'm just going to use c because we're using critical values. We have 3 factored out, c squared minus 18 divided by 3 is 6, c plus 5 equals 0. Okay, so we could divide by 3 just to get rid of it, but it doesn't bother us. Really what we want to do is factor this term over here. We have c squared minus 6c plus 5. So to factor this, it's product sum. So two numbers that multiply to give us 5 and add to negative 6. So product sum, two numbers that multiply to give you a times c, so the coefficient of the first term, so the number in front of the c squared is a 1. The number in front of the that's alone is a 5. And the same two numbers that add to give you b, which is the term that's over here. So not 6, it's minus 6. Make sure to take the sign in front. Don't forget that. So you want two numbers that multiply to give you 1 times 5, which is 5. And the same two numbers that when you add, they give you negative 6. So the only, what works here? Two numbers that multiply to give 5 and 6. So write down the factors of 5. All you have is 1 and 5. So these numbers here have to be 1 and 5. But when we multiply them, they have to give us 5, but when we add them, they have to give us negative 6. To get negatives, you have to ensure that both of them are negative. So negative 1 times negative 5 is positive 5, and negative 1 plus negative 5 is negative 6. Those are the factors. So we get 3, c minus 1, and then c minus 5. Okay, so we factored these two terms. Now we use the zero product law. Two numbers that multiply to give us 0. The only way for that to be possible is if either this number here is 0 or this number here is 0. So either c minus 1 equals 0 or c minus 5 equals 0. So we get c equals 1 and c equals 5. Okay. Next thing that's really important to verify is that your critical points here, do they lie in the closed interval that's given over here? We got 1 and 5. Are those between 0 and 6? Yes. So we include these values. We're going to use them. Okay. So this is step 1. You found your critical values that lie in our interval. Great. Step 2 is to check the endpoints. So let's go ahead and check all the endpoints of the critical values and the endpoints at the same time. So let me just erase and do that. Okay, so now we're checking. So what we have to check is the critical points and the endpoints. So check endpoints and critical points. Notice that we didn't check when f prime of x does not exist because we're talking about a polynomial function. So there's no division of 0, so there's no cases where the derivative doesn't exist. It's continuous and differentiable, so we're okay. So for the endpoints, what we have to do is check f of 0. That's the first endpoint. That's 0. And then we have to go find f of 6. See what those values are. For the critical points, we have to go find f of 1, and we have to go find f of 5. So we plug in the critical points and we plug in the endpoints back into the original function. That's all we're doing. And then out of all those options, we take the one that's the highest and we take the value that's the lowest. And that's the game plan. That's the closed interval method. So let's go ahead and do that. F of 0, if you replace 0 into the original function, not the derivative, you get just -5. If you plug in 6 into the original function, so 6 cubed minus 9 times 6 squared plus 15 times 6 minus 5. Let me use a calculator. So 6 cubed minus 9 times 6 squared plus 15 times 6 minus 5. I got -23. Let's plug in 1, so you get 1 minus 9 plus 15 minus 5, giving us 2. And when you plug in 5 into the original, 5 cubed minus 9 times 5 squared plus 15 times 5 minus 5, I got -30. Okay. And from this, we're able to decide what's the absolute max, what's the absolute min. So the absolute max, the biggest value we got, occurred at 1, and the absolute min occurred at -30. So this is the absolute min, and this is the absolute max. And we're done. That's the answer. So in example number 2 over here, we have to find the absolute max and min of the function f of x equals x squared over x plus 4 on the interval, the closed interval, -3 to 4. Okay. So pause the video, try to do it on your own, see if you can get the right answer. So the first thing that we need in order to apply this is we need the function to be continuous on our domain. Is the function continuous? Well, f of x equals x squared over x plus 4, it's not continuous, right? Because if I replace x with -4, we're dividing by 0 here. We have a division by 0, and that's an issue. So remember, the function that we're working with has to be continuous. But we do have, although it's not continuous, it is continuous on the interval. So the issue here occurs when x plus 4 equals 0, meaning that x equals -4. But is -4 on our domain, on the closed interval that we're working with? No, it's stopping at it starts at -3 and goes to 4. So -4 is outside that interval, so we're okay. Okay, but you do have to ensure that the function is continuous. So continuity on the domain, on the closed interval, which is what we have. So it's continuous on our domain, great. We have a closed interval, great. So we're ready to go ahead and use the closed interval method. So we start off by finding the critical points. Let's go and do that. So the critical values, we get them by taking the derivative and setting them equal to 0. So we're doing f prime of c. I'm just going to replace the x's with c. And here what we're doing is we have a fraction, so we're using quotient rule. So recall quotient rule, f over g. Derivative of the top times the bottom minus the derivative of the bottom times the top over bottom squared. Okay, so the derivative of the top is 2x, but I'm just going to use letter c, times the bottom minus the derivative of the bottom, which is 1 times the top. Again, instead of x's, I'm using the letter c. Don't let that confuse you. Oops. So here I should be using c, not a hex. And then over the bottom squared, so c plus 4, all that squared. That's our derivative. Let's go ahead and simplify that. So what we get here is, I'm going to distribute the 2c, giving me 2c squared plus 8c minus c squared over c plus 4, all that squared. And 2c squared minus c squared is c squared plus 8c over c plus 4 squared. Now what we can do is factor out a c on top, giving us c times c plus 8 over c plus 4, all that squared. So the critical value occurs when the derivative is equal to 0, so we focus on the numerator. So case 1, f prime of c equals 0. So if we look at the numerator, we have c times c plus 8 equals 0. So we're using the zero product law. We're multiplying two terms and it's equal to 0. So the only way for that to be possible is either the c has to be 0 or the c plus 8 has to be 0, right? You're multiplying two numbers and it's equal to 0. Only possible if one of those two numbers is a 0, or both. So we either have c equals 0 or we have c plus 8 equals 0. Which means that if we bring the 8 over, c is equal to negative 8. So we have c equals 0, c equals negative 8. Those are our two critical values. But we're not done. We have to check when the denominator is not equal, when the denominator doesn't exist. So let's go ahead and do that. So denominator, sorry, when the denominator is equal to 0 or when the derivative doesn't exist. So we're checking when c plus 4 squared equals 0. If we square root both sides, we get c plus 4 equals 0. And bringing the 4 over, subtracting by 4 on both sides, we get c equals negative 4. Okay. So these are the three critical values that we have. Okay. What I would do next is, don't stop here, don't plug in these values. Verify if these critical values are in our domain, in our closed interval that's given, from negative 3 to 4. So 0 lies in our domain, but negative 8 doesn't, so you can reject it. Don't use it. Because if you plug this back into the original function and you get a larger, an absolute max or an absolute min, it's actually incorrect. We reject it because it doesn't lie in our closed interval. The other thing is c equals negative 4. Again, this does not lie in the interval that's given, so we do not use it. All we have really is the critical point that c equals 0. So that's the only one that we have to verify. And on top of this one, step 2, we have to verify the endpoints. Okay. So let's erase this and let's go ahead and do that. So now we're checking. So really what we're looking for is f, the critical point. And then we're going to check for f at the endpoints. F of negative 3 and f of 4. Okay, so these two here on the bottom are the endpoints and the one on top is our only critical point in our domain. So if we replace the x's with 0 into the original function, we get 0 squared over 0 plus 4. We have 0 over 4. So 0 divided by 4, don't get confused. It's not 4 divided by 0. So this is just 0. Okay, it's not infinity. It's not undefined. We have 0, which is being divided by a number. This is just 0. Okay. F of negative 3, let's plug in negative 3 into here. So it gives us negative 3, put it in brackets, squared over negative 3 plus 4. Negative 3 in brackets squared is positive 9. Don't get confused with that. And then negative 3 plus 4 is just 1, so this gives us 9. And then f of 4 is 4 squared over 4 plus 4, giving us 16 on 8, which is 2. So this means that at 0, the y value of 0 is the absolute min. And at 9, at the critical point, negative 3, sorry, the critical point 0 was an absolute min, and the end point, negative 3, gave us an absolute max. So here the absolute max occurred at an end point. Okay, and those are our answers. Okay, so in this example here, very similar. Find the absolute max and min of the function f of x equals ln of x over x on the interval from 1 to 4. So pause the video, try to do this on your own, see if you can get it. First things first, we have to verify, we have to ensure that the function is continuous. Do we have a continuous function here? No, we do not. Why? We can't divide by, we have a division and we can't divide by 0. Is 0 in the interval? No, so that's fine. Good. So it's not continuous, but it is continuous so far in our interval because 0 is not in the interval. What about the ln of x? What can't we have? What can't we replace into the x for logarithmic functions? Well, that answer is 0 or any negative number. Plug that into your calculator. If you plug in a negative, like ln of a negative value, you're gonna get an error message. So ln is only defined for positive x values. But that's okay because our interval is from 1 to 4. It's only positive values, so we're good. So the function is continuous on its domain. So we have continuity, we have a closed interval, we can use our closed interval method. So we start off by finding the critical values. So solution f prime of c. So I'm just going to replace my x with c. So when I'm taking the derivative, we have a fraction, so we're using quotient rule. So we're going to take the derivative of the top. So the derivative of ln of x is 1 over x, but I'm using the letter c. So 1 over c times the bottom, x is being replaced with c, minus the derivative of the bottom, which is 1, times the top, ln of c. All that over the bottom squared. Okay. So 1 over c times c, they cancel each other, leaving us with 1, minus 1 times ln of c is ln of c, over c squared. So next, what we have to do is set this equal to 0. So we want to know when the numerator is equal to 0. So we have 1 minus ln of c equals 0. So we're going to solve for the c, starting off by bringing over the negative ln of c on the right side, turning it positive. So we're adding ln of c on both sides. So 1 equals ln of c. And next we want to get rid of the ln. How do we get rid of ln? Well, we raise both sides to the e. Or you can use the Napier formula. But I generally think of it this way. So notice that these 1 equals ln of c is now in the exponent of the e. So on the left hand side we have e to the 1, which is just e. And on the right hand side of the equation we have e to the ln of c. Well, this is a log property. If e matches the base of the logarithm, which ln is log base e, the answer is just what's in the brackets. So this is just equal to c. Okay. So e is the value 2.718, and that's our critical value from the numerator. Okay. So now what we have to do is check the denominator. So recall, I'm using the numerator and the denominator because numerator equal to 0 is when f prime of c equals 0. And the case when the denominator is equal to 0 is really when f prime of c does not exist. So those are our critical values. When f prime of c equals 0, we focus on the numerator when you have a fraction. And when f prime of c doesn't exist, you're essentially looking at the denominator. So the denominator here, we have c squared, and we're setting that equal to 0. Square root both sides gives us c equals 0. Okay. So we have c equals e and c equals 0. Do these two values lie in our domain? No. C equals e is 2.718, so that does lie. We're going to use this one. But c equals 0 is not in our domain. So we're going to reject the c equals 0. So all we have to do is verify c equals e, and then the endpoints 1 and 4. So let's go ahead and do that. So we're verifying. We're verifying the critical point, so we're going to look for f of e. We're plugging e back into the original function that's given, not the derivative. And we're going to plug in the endpoints 1 and 4. When we plug in e, we get ln of e over e. Giving ln of e is just 1 over e. Plugging in 1, we get ln of 1 over 1. And ln of 1 is just 0. And then 4, we get ln of 4 over 4. This one, we're going to use a calculator just to get the actual values. 1 over e is about 0.367879. This is 0. And then ln of 4 divided by 4 is about 0.3465. So on and so forth. Okay, so from this we see that at 1, the first endpoint, we have our not our local, an absolute absolute min. This is our smallest value. And at what's our largest? This one's larger. 0.36 exceeds 0.34, so we have our absolute max at E, our critical point. Okay. So if you got this, great job. If not, we'll keep practicing. Okay, so in this example over here, we have to find the points where we have horizontal tangents. So we're looking at this new term, horizontal tangents. What is that? And they give us the function f of x equals x to the 4 minus 8x squared plus 14. So notice here we don't have closed intervals, so we're not using closed interval theorem. We have to figure out what they want or what they expect us to find when they say horizontal tangents. Well, let's think about it. If we have a function, what's a horizontal tangent really? So just consider the function, I don't know, some function like this. Well, our horizontal tangent is just a horizontal line, and the tangent, it touches the function at one point, so that would happen at the max. So this is what we want to find. We want to find the red line, essentially the equation of the tangent line. But what do we know about the slope here? We know that the slope is 0. If it has a horizontal tangent, the slope is 0. And we know that the tangent is really the derivative. So what it's asking us is really, when is the derivative equal to 0? So when they ask for a horizontal tangent, they're actually asking when is the derivative equal to 0. This is what we're looking for. We're looking for this point, C, and then they give it as C f of C. Okay. So we're looking for the point where we have a horizontal tangent given this function here. The example I drew is a quadratic. We don't have a quadratic, we have x to the 4. Let's go ahead. I won't be able to draw it, but let's go ahead and find the answer. And then you can use decimals as a way to compare your answers with what you get. Okay. So when they ask for a horizontal tangent, they're essentially asking when is the derivative equal to 0. Okay. So keep that in mind. So let's go ahead and take the derivative of the function that's given and set it equal to 0. So f prime of x, I'll use the letter c. F prime of c is 4c cubed minus 16c plus 0. Okay, so we took the derivative, we're going to set it equal to 0. So now what we have is we could factor out of 4c, leaving us with c squared minus 4 equals 0. At this stage here, you can use the zero product law, but let's factor further. We have c squared minus 4. It's a binomial with a minus. So when you have two terms with a minus in between, you should ask yourself, could you square root both terms? In this case, you could. So this is a difference of squares. So we could write this as 4c times the square root of c. I always open two brackets right away. Square root of c squared is c. The square root of 4 is 2. One's a plus, one's a minus. Okay. And now I use the zero product law. So if you're multiplying three terms and it's being equal to 0, well, at least one of the three terms has to be a 0. So either, if not all three, either 4c equals 0, or the c plus 2 equals 0, or the c minus 2 equals 0. This means that 0, dividing both sides of the first equation by 4, you get c equals 0. C plus 2 equals 0, we're going to bring the positive 2 over, it becomes negative, you get c equals negative 2. And then here we have c, we bring the negative 2 over, we get c equals 2. It becomes positive, and we have these three values. So we have, so for this quadratic, not quadratic, for this function over here, we have three critical values. C equals 0, c equals negative 2, c equals 2. But it's asking us for the point. Find the points where we have horizontal tangents. So let's go ahead and for each value, substitute it back into the original function and get the entire point. Okay. And this is going to be where we have horizontal tangents. So for the first point, for c equals 0 or x equals 0, f of 0, the original function, we're plugging it into here. So 0 to the 4 minus 8 times 0 squared plus 14 is just equal to 14. So we have a horizontal tangent at the point 0 and 14. That's one of them. Let's go get the second. Let's plug in negative 2. F of negative 2. So we're plugging into the original function, not the derivative. So you get negative 2 to the 4 minus 8 times negative 2 squared plus 14. This gives negative 2 to the 4 is 16 minus 8 times negative 2 squared is positive 4. 4 times negative 8 is negative 32. And then plus 14. 14 plus 16 is 30 minus 32. This gives us negative 2. So the second point where the tangent occurs is the point -2 and -2. Okay. Lastly, we have to check the value +2. So f of 2 is equal to 2 to the 4 minus 8 times 2 squared plus 14. That gives us 16 minus 32 again plus 14, giving us -2. So the other tangent occurs at 2 and -2. And these are the three values, or the 3 points where we have a horizontal tangent. Okay. Let's take a look at another example. So in this example here, we have to find the points where we have horizontal tangents given the function. So points, it could be one or multiple. So let's put the s in brackets. Given this function here, f of x equals x minus 2, all that to the 4, times 2x minus 3, all that to the 5. So pause the video, try to do this on your own, and see if you get the same answer as me. Okay. So keep in mind, horizontal tangent, we know that's when the derivative is equal to 0. So we'll keep that in mind. So let's go ahead and do that. Let's take the derivative of this function here. So what you have to catch is that it's a combination of product rule and chain rule. So we have a multiplication, so it's product rule, and chain rule because of the exponents. You might be able to use a logarithmic differentiation to solve this. That might work and it might be faster, but I'm going to go ahead and use product rule. So taking the derivative f prime of x, what we get is, remember, product rule is f times g prime. When you're taking the derivative of two functions which are multiplying, it's the derivative of the first times the second plus the derivative of the second times the first. Okay. So the derivative of the first term, this is our first term, this is our second term. The derivative of the first term, we're going to use chain rule, drop the 4, x minus 2, subtract the exponent by 1, gives us 3, and then take the derivative, multiply by the derivative of the inside. So the derivative of x minus 2 is just times 1. And now we leave the second function, 2x minus 3 to the 5. So this part here, the first part's done, plus, now g prime, we take the derivative of the second function. So the derivative of the second function is, we're going to drop the 5, leave what's in the inside of the bracket, subtract the exponent by 1, and then after we're going to multiply by the derivative of the inside. The derivative of 2x minus 3 is just 2, so times 2. And then we leave the first function, so x minus 2 to the 4. Okay, so here we're done. This is our derivative. Let's go ahead and simplify this. So we can rewrite it as 4x minus 2 cubed, 2x minus 3 to the 5, plus 10, 2x minus 3 to the 4, x minus 2 to the 4. Okay. So we got this by simplifying. I just took the 2 and the 5 and multiplied it, the 4 and the 1 multiplied it, and that's it. Next, what we have to do is factor out the common terms between the first and the second term. So what we're going to do first is factor using GCF. So look at the numbers first. We have a 4 and a 10. What do they have in common? What could you factor out? Well, they're both even, so we could factor out a 2. A 2. Now if we look at the x minus 2 term here and the x minus 2 term here, we have x minus 2 to the 3. Here it's x minus 2 to the 4. The most you could take out is the lowest exponent, so you could take out 3 of them. x minus 2 cubed. And then if we look at the 2x minus 3's, here there's 5, here there's 4. So the most we could take out is the lowest exponent, so we could take out 4 of them. So 2x minus 3 to the 4. Open bracket. If this is what we pull out, what's left over? So we had 4, we took out 2, or you divide it by 2, we're left with 2. X minus 2, we took out 3 of them, and there was 3, so there's none left. And we took out 2x minus 3 to the 4, and we had 5 of them, leaving us with a 2x minus 3. Plus, next term, we took out a 2 from the 10, or we divided by 2 from the 10, leaving us with 5. 2x minus 3 to the 4, we took out 2x minus 3 to the 4, we took out all of them. And then the x minus 2 to the 4, we took out 3 of them, leaving us with 1 x minus 2. Okay, so let's go and simplify. We had 2 x minus 2 cubed, 2x minus 3 to the 4, and now here we'll distribute. So we get 2 times 2x, and then we'll multiply the 5 in. 2 times 2x is 4x minus 6 plus 5x minus 10. Simplifying this, we get 4x plus 5x is 9x, and negative 6 minus 10 is negative 16. So I'm just going to write 9x minus 16. And remember, the game plan for the horizontal tangent, take the derivative, set it equal to 0. We took the derivative, we got this, we simplified it, set it equal to 0. Next, all we do is zero product law. So if you're multiplying all these terms and it's equal to 0, well, that means either the first term, the second term, or the third term has to be equal to 0, or more than 2 terms. Only the 2 here can't be 0, that's obvious. So either the x minus 2 equals 0. You could put the cube as well if you want, but you're just going to cube root it, so it doesn't really matter. So x minus 2 cubed equals 0. 2x minus 3 to the 4 equals 0, or 9x minus 16 equals 0. Okay. So like I said, the cube, you could cube root both sides, so you're just going to remove the roots. That doesn't affect it. And then the x minus 2 equals 0, you just bring the minus 2 over, you get x equals 2. Okay, so x equals 2, that's the first x value. Here we have 2x minus 3 to the 4 equals 0. We're going to take the fourth root, so that cancels out the 4 here. And then we're going to bring over the negative 3 becoming positive, and at the same time divided by 2, giving us x equals positive 3 over 2. Okay, that's the second value where we have a horizontal tangent. And now here we're going to just bring over the negative 16 and divide by 9, giving us x equals 16 over 9. That's the third value. And then the last step is just to substitute these values back into the original. Okay. Because again, it's asking for the points. If it was asking just for the x values where there's a horizontal tangent, then we're done. These are the 3 x values. But since it's asking the points, let's go ahead and find all the points. So the first one, we're looking at when x equals 2. When x equals 2, f of 2, right away, if we plug in 2 into the first thing, we get 2 minus 2, which is 0, so the whole thing is just 0. So the first point is 2 comma 0. That's where we have a horizontal tangent. The next one is 3 over 2. So when x equals 3 over 2, f of 3 over 2, this I will need a... Oh no, we could plug in the 3 over 2 over here. So 2 times 3 over 2 minus 3. Here, 2 times 3 over 2, the 2's cancel, leaving us with 3 minus 3, which is 0. So this piece here is going to give us 0. And 0 times this is just 0. So the second tangent is at 3/2 comma 0. That's done. And now the third horizontal tangent occurs at x equals 16 over 9. And this one will need a calculator. So if we look for f of 16 over 9, we plug in 16 over 9 into here. What do we get? So 16 over 9 minus 2 to the 4. I'm getting 16 over 65, 61, multiplied by 16 over 9 times 2 minus 3 to the 5. And then that answer times 16 over 6561. Okay, so a very small number. So I'm getting about 0.000129. So a value that's very close to 0, but not quite. Okay. So the point is 16 over 9 comma 0.000129. Okay, and that's the horizontal tangent. So I hope these videos help.